Hi, today we are going to be reviewing vectors. So first thing we're going to do is look at the difference between scalar and vector quantities. So scalar quantities are quantities that express only magnitude. So these would be things like mass, voltage, power. So I've got as examples distance, mass, voltage. So 2 kilometers, 2 kilograms, 120 volts, all those measurements would be scalar quantities. Vector quantities, on the other hand, also have magnitude, but they also have direction. So things like displacement, velocity, forces, momentum, anything with a direction is a vector quantity. So for example, 2 kilometers west, 27 meters per second north would both be measurements that are vectors because they include direction. Now, in our textbook, scalar quantities are usually represented by regular case variables, while vector quantities are represented by bold variables or variables with an arrow over them. So for example, if we had, say, distance, which is scalar, our textbook would have a symbol like that, where displacement, which is a vector, we would have something much more bold looking or having an arrow over top of it. So that's just notation to know when reading through your textbook. Now, vector diagrams are drawn by drawing out our vectors with arrows. Now, if the arrows are representative of our vectors in that the direction the arrow goes is the direction our vector goes, and the length of arrow is representative of the magnitude of our vector. Now, often vector diagrams are drawn to scale. Now, if we're adding vectors in 2D, we want to draw a diagram utilizing the component vectors, drawing them head to tail. So for example, that means that if this is our first vector, our second vector would start there. So we have the head of one arrow to the tail of another vector. Now, if we have two vectors at 90 degrees, we use Pythagoras to solve for the resultant or hypotenuse. Now, most of you are in grade 12, so you will have used sine law and cosine law, so you would also be able to solve ones where they do not make a 90-degree triangle using those laws. We also use trig to find the angle from where you started. So we'll look at an example. You walk around a bog by going 5 kilometers east and then 15 kilometers north. We want to know what your displacement from where you started is. So I've drawn in the first vector they gave us, so 5 kilometers east. And then I'll draw in the next one. Now 15 kilometers north is 3 times the magnitude, so I'd probably try to draw an arrow that's 3 times the length. And then from where we started to where we ended would be our resultant, which I've drawn in red. And we also want to figure out that angle. So our resultant would be our displacement, its magnitude, and our angle would be our direction. So because we're dealing with just east and north here, we know those are 90 degrees to each other, so we can just use basic Pythagoras. So c squared equals a squared plus b squared, where we know if we take the square root of both sides, we get c equals the square root of a squared plus b squared. Substitute our values in. We get 15.8 kilometers, but going to appropriate sig figs, we end up with 16 kilometers. Now, technically, we know all 3 sides of our triangle, so we could use any of our 3 trig ratios. However, because we've rounded our hypotenuse, I would tend to stay away from using our hypotenuse and instead just use the 2 original sides given, which also, if we made a mistake getting our hypotenuse, we could still get our angle correct even though our hypotenuse was incorrect. So I would use our two original sides, which would be an opposite side and an adjacent side, so that would be utilizing tan. We then want our angle on its own, so we have theta is arctan of 15/5, which gives us 72 degrees. Now we have to reference that still. That 72 degrees, if we look at our diagram, is measuring off of our east line, and it's going to the north of that. So we say that 16 kilometers, 72 degrees north of east. Now we did use vectors in Physics 11 a fair amount for distances and displacements, but we also used them for free body diagrams. So this is a diagram of any object in which all forces acting on it are drawn with vectors. So in this case, we would have one of these vectors is our force normal, one's a force normal, force normal, force friction, and force of gravity.